I'm sure all of you are interested in climate change and realise how much of a problem it is, and that we need to address the issues involved. What I hope to describe this evening is how climate models can help us to understand how the climate is changing and how it might change in the future, and what we can do about it to stop damaging climate change. Now, I'm going to give you a little bit of information about the history of weather and climate forecasting, just to give you some background. It's always been very much the science around weather and climate has always been very much about solving real world problems, helping people to respond to real events. The UK has always been at the forefront of weather and climate science. It's got the longest climate record, for example, in the world, going back to the 1650s, which gives us a very good insight into the way that climate has changed in the UK. It's the Central England temperatures, which you'll sometimes hear the Met Office talking about when they talk about temperature records. Admiral Fitzroy was one of the pioneers of weather forecasting, and his forecasts were really based on his empirical understanding of how the weather behaved when he was at sea. Fitzroy is also well known because he was captain of the Beagle, which was the ship that Darwin sailed on to when he went to the Galapagos, and they had a kind of interesting relationship which you can read about. It's not really relevant to this talk, but Fitzroy was a remarkable man, incredibly difficult though. But just looking at the chart in the middle there, this was an October storm in 1859 that led to significant losses at sea, because obviously people didn't know it was going to happen. And after that, there was agreement to produce shipping forecasts in the Times newspaper, which Admiral Fitzroy produced on behalf of the Board of Trade. And with some interruptions, those forecasts led through to the forecasts that we have today. It's worth bearing in mind that the Thames freezing over in 1895. This was one of the coldest winters on record, and it's not something we're likely to see again, of course, with the warming of the climate. There are obviously other changes that have happened with the Thames, as well as changes in climate. Moving on to some of our understanding about how the weather behaves and how that impacts the way that we model the climate. One of the things that Fitzroy pointed out was that I need hardly to repeat, sir, what has been so often explained, that the forecasts are expressions of probabilities and not dogmatic predictions. So even back in 1863, he was trying to explain to people that what probabilities meant, and that forecasts, as you go further into the future, are going to be much more uncertain. Of course, his forecasts, he didn't have any of the computers that we had. He didn't have the science that we have to give him the accuracy. And so they were much more expressions of probabilities. But he did have a lot of fights on his hands, because people said, oh, you mustn't make these forecasts because they're so misleading. But eventually they were reinstated. So this expression about probabilities was really thought about in a scientific way, largely from the work of Ed Lorenz in 1963, and this developed into the science of chaos theory. Weather was one of the first applications of that. And he said, one flap of a seagull's wing may forever change the future course of the weather. So that gives rise to the issue that we can now get fairly good understanding of what the weather's going to do in about a week ahead. Although, if you were predicting a storm at the weekend, you probably would need to look much nearer the time to get the details and make sure it was actually going to happen. But once we get to 2 or 3 weeks ahead, it's really much more difficult, particularly in the mid-latitudes where we live. So how can we predict climate, which is obviously looking at what happens over a timescale of 50 or 100 years? Well, climate and weather are not the same thing. Climate is what we expect, and weather is what we get. That's one way of phrasing it. This has been ascribed to Mark Twain. He didn't actually say it, but anyway, it's a nice summary of what we mean. So the climate is things like the average temperature, the average rainfall, but also the frequency of storms, the frequency of droughts. So it tells us about the statistics of the weather, the averages of the weather. It doesn't tell us about what the weather's going to be on the 2nd of February in 2053. it tells us those averages. So what we're seeing, though, is evidence that the climate is changing. So we no longer know what to expect. So there are changes in the number, frequency, and strength of weather events over a long period of time. So what we're able to do is, looking at observations, we can observe these things happening, and then we need to use models to interpret the science to understand why they're happening. And to disentangle whether there are natural changes or man-made changes, or what it is that's going on. So I think always the science has been a little bit ahead of our ability to actually interpret that science, to get numbers out, to get the answers. And those numbers coming out are really very dependent on computers. The science that we're using is what we call nonlinear, which means that we can't solve it on a piece of paper. We need vast amounts of data, we need complex equations, and we need computers to put those things together and to come out with the answers. So the first computers that we used, this is one that was used by the Met Office for weather forecasting, were in 1959. They were very, very crude, obviously, nowhere near powerful as anything that you use, probably even your washing machine today. And so the versions of the equations that were solved were actually very simplified, because that was all that could be solved. But nevertheless, it was the first step. What's interesting is a lot of the step changes in capability of weather forecasting have been in response to extreme events. So 1953, there was the big storm surge in the North Sea, causing catastrophic flooding in southeast England and killing 307 people. And this obviously led to the construction of the Thames Barrier, but it also led to the development of the Storm Tide Forecasting Service, and the ability to produce weather forecasts obviously was central to that. Equally, some of you will remember the storm in 1987, which was very severe in southeast England, and it was the one which Michael Fish said was not a hurricane, which is strictly true. It was not a hurricane. Hurricanes happen in the tropics, but it was the remnants of a hurricane that turned into an extremely strong storm. And the Met Office didn't forecast that very well. And as a result of that, they had a big increase in supercomputer power and a big investment in the science of weather forecasting. So they were able then in the future to produce much better forecasts, and that has continued obviously over time. The next big challenge, and moving on to climate change now, it was widely appreciated that climate change was an issue and that we needed to understand how the climate was changing. And Margaret Thatcher was very keen to support the science and make sure we had a good understanding of how climate was changing, so that the UK could contribute at the political level to the debate about what we needed to do about it, and opened the Hadley Centre at the Met Office in 1990. And the climate models had a big input in development at that stage to get that understanding. It was in 1992 that the Rio Earth Summit took place. So you can see that these things were very closely linked. And next to Margaret Thatcher was John Horton, who died about a year ago, but he was the chief executive of the Met Office at the time, and then he became the co-chair of Working Group 1 of the Intergovernmental Panel on Climate Change. So you can see how embedded the Met Office and the UK science was in those early days, and still is in the understanding of climate science and climate change in order to inform the political debate. So I'm going to come now to the science and what we need to represent in a climate model. So this is a kind of graphic that shows the key processes that are important in driving the weather and climate. So we have the energy cycle, the water cycle, general circulation, and the things that can change those things. And I'm going to go through each of one of these in turn. So without the sun's energy, of course, we wouldn't have we wouldn't have life on the planet. We wouldn't have the climate balance that we have. So we have incoming energy from the sun. The sun's energy it's reflected by clouds. It can also be reflected by the earth. Some of the energy is absorbed by the atmosphere, and some of it's absorbed at the surface. The heat that's generated is then re-radiated from the earth, and that heat passes through the atmosphere and So what you're getting is a balance between energy coming in and energy going out. There are different wavelengths because the sun's obviously much, much hotter, and so that comes in at much shorter wavelengths, ultraviolet wavelengths, and from the Earth it's much cooler, so it's going out to infrared radiation. And so the way that that energy and radiation interacts with the atmosphere is quite different, and the way that it interacts with clouds is quite different, for example. So what happens is that as the infrared radiation is absorbed in the atmosphere, it warms up the atmosphere. If you have more greenhouse gases in the atmosphere or other more greenhouse gases in the atmosphere, then they can absorb more of that radiation and acts a bit like a blanket or a duvet, keeping the lower atmosphere warm. So what happens as the greenhouse gases increase is the lower atmosphere gets even warmer and the upper atmosphere gets cooler because it's being shielded from that infrared radiation. And that's the pattern of change that we're seeing. So the most important greenhouse gases are water vapor and carbon dioxide, and there are various others like methane. So water vapor is obviously naturally occurring, and that tends to balance out in the atmosphere. The big change that we're making is in changing some of the other greenhouse gases, in particular carbon dioxide. So what happens when carbon dioxide goes up? Actually, I'll just go on to the next slide to illustrate that. Oh yes, before I say that, so it's acting like a duvet. If the greenhouse gases weren't there, then the temperature of the Earth's surface would be minus 18 degrees on average, whereas actually plus 15 degrees. So greenhouse gases are really important. We need them. What we don't need is a rapid change in them. And obviously at minus 18, there would be no life on Earth. So just going back to the water cycle before I talk about the importance of water vapor. So as the Earth heats up, water evaporates from the rivers, lakes and oceans, and from the Earth's surface and from vegetation. The water condenses to form, as it cools down, the water condenses to form clouds. The water returns, so once the clouds get saturated, the water particles become heavy and you get snow and rainfall falling back to the ground and down through the rivers, and obviously you get obviously there's a cycle there. But that, as I mentioned before, the water vapor is also a greenhouse gas. So you can imagine if you warm up the Earth and the atmosphere, you're going to get more water in the atmosphere, which is exactly what happens. And that water then heats up the atmosphere even more. So it's what we call a positive feedback. So by positive feedback, we don't mean a good feedback in this context. We mean it's enhancing the effect. So, for example, if you double the amount of CO2 in the atmosphere, so if you increase the temperature by 1 degree in the atmosphere from CO2, it almost doubles it to an increase of 2 degrees with the increase in water vapor. So it's a big impact, and it's this kind of natural feedback that can change the amount of warming. So the other thing that happens in the climate system is that there's this general circulation, and because the Earth is spinning, you get these cycles, the Hadley cell, Ferrel cell, and polar cells, for example, and you can see the winds. Hopefully, you can see the cursor here, with the winds are not blowing from the equator, from the pole to the equator, or the equator to the pole. They actually blow at an angle because the Earth is spinning, but that redistributes the heat around the world. The same sort of thing is happening in the ocean. The ocean actually has got a very large heat capacity. So in fact, a lot of that heat is stored in the ocean and is distributed in the ocean. So the way the oceans work is really important. When you look at a short-term weather forecast, you're really worried about what's going on in the atmosphere. When you're looking at a climate prediction, you really need to know what's going on in the ocean as well, because so much of the action is happening there. And so we can't just take the atmosphere, we have to look at the ocean as well. So it's an extra complication when you're looking at a climate prediction. So, so that's rebalancing the heat across the globe. And one of the things that happens, obviously, is when you change the balance by changing the amount of greenhouse gases, is that then will then change the weather patterns and change that circulation, because it will try to rebalance itself again. So we can get increases in storms, for example, or decreases in the storms, movements of jet streams. So, for example, a lot of our weather in the UK where we get storms is influenced by where the jet stream is. So if that moved north, for example, towards Iceland, we might get fewer storms and more dry weather. Whereas if it moves south, we might get more storms and more wet and windy weather. So it's really important to be able to understand those things as well. It's not just about the global average. It's very much about those sort of details. So you can see, I think, that if you change one thing, then that will change everything. So the thing that we're changing at the moment is the amount of carbon dioxide, methane, and other greenhouse gases. We're also changing something we call aerosols, and I'll come back to this later. So some of the particles that are produced when you burn fossil fuels, things like nitrous oxides, can affect the atmosphere as well as being pollutants that are harmful to human health. They also affect the atmosphere. In particular, they can act as nuclei for clouds. So basically, in some cases, clouds can form more in those circumstances, and that can actually, in some circumstances, lead to a cooling of the atmosphere. So some of these things are offsetting each other. So if you clean up the aerosols, you actually increase the amount of warming. Obviously, we want to clean up the aerosols, but we need to understand that balance in order to understand what the impacts are going to be. So now I'm going to talk about some of the observations that we've seen of the climate system. And so obviously, if we want to go back before the historical record, we have to use what we call proxy data. So what we have here is the measurements of ice cores in the Antarctic ice, and you can see the ice core here. And what they do is they can measure the amount of CO2 in those ice cores. They can also measure the age of that CO2. And from that, they can get a graph of how the CO2 is changing. And you can see along here, there are fluctuations on timescales of tens of hundreds of thousands of years. And then on the right-hand side, you'll see what looks like a vertical axis, but in fact, that's the change since the Industrial Revolution. It's so rapid that it looks as though it's completely vertical. My husband suggested that I put that star on there to highlight the fact that this wasn't just the axis, this is actually the change in carbon dioxide. So we're making very big changes very quickly, and it's that scale that is what we need to understand, whether that's causing us a problem, and we think that it is. So going to actual direct observations now, there have been observations of carbon dioxide from the Mauna Loa Observatory in the Pacific since the late 1950s. What's interesting about this is that getting funding for these measurements over a period of time has been very difficult. It's much easier now, of course, because you recognise its importance. But a lot of scientific funding is short-term and is based around new and exciting science. A lot of climate observations require very long records with very consistent records, or at least if you make a new type of observation, you need to be able to relate it to the old one so that you can actually look at a time series. So, it was really down to Keeling and later to his son that they were really persistent in making sure that these measurements went ahead. And it is really because people are so, a few people were very dedicated at these times to make sure that we have these observations, which are really valuable to us. And you can see the very clear increases in carbon dioxide since the late 1950s. It's increased by around 35% since 1958. This slide is probably a year or so out of date, but you get the picture. And equally, the global temperature has increased by more than 1 degree centigrade since 1850. Another thing to note about this graph is that this is produced by the Met Office, and one of the things that they do is to look at the uncertainties in the measurements, because if you go back to 1850, of course, we didn't have very good measurements. We didn't have very many measurements compared to what we have today. And so you can actually assess the uncertainty and the inaccuracies, if you like, in the global assessment and capture that on your graph by the grey shading which shows that range. But you can see even with that uncertainty, it's very clear that the temperatures have increased rapidly, particularly since the 1950s. And the other thing that carbon dioxide does is it gets absorbed into the ocean, which is a good thing from a climate point of view because it slows down the warming. So some of that CO2 is being absorbed in the ocean, some of it's being absorbed in the plants and soils on land. But the downside is that the oceans are 30% more acidic, threatening marine ecosystems. And one of the obvious ones is obviously coral reefs, but obviously there are many others as well. So what have we seen? I mentioned that one of the things that we see characterizing the climate is extreme weather, and weather events. And so this diagram attempts to show the changes in extreme weather and that they've become more frequent and more severe. And it uses geophysical events to compare with. So the red line, the red bars along the bottom here, are things like earthquakes, tsunamis, and volcanic activity. And you see they fluctuate from year to year, but they haven't gone up. Whereas if we look at the climate-related events, they have changed. So we look at the meteorological events, so that's things like tropical storms, local storms, convective storms, and you see that those have increased over time. We look particularly at hydrological events, so floods and mass movements of water. Those have made a big increase over time. And wildfires, drought, extreme temperature have also increased. So can we link those changes to climate change? So one of the things that we can do is use climate models to mimic what happened in the atmosphere in reality over the last 100 years, using all of the observations of carbon dioxide and so on. And then we can also do it assuming that the carbon dioxide and the other greenhouse gases stayed at pre-industrial levels. And using that, we can get an assessment of how much of this change we can ascribe to climate change. So we can say that more than 60% of extreme events studied to date were made more likely or more severe by man-made climate change. So this is a good example of how we're using observations and climate models to help us understand how the climate has already changed and how much of that is down to man-made climate change. So what is a climate model? So this is the same sort of picture I'd show for a weather model. In fact, we use the same models for weather and climate forecasting. So we obviously we have to use these. We can't tell what's going to happen in 50 or 100 years' time unless we use a model to represent it. So essentially what they're doing is they're representing our understanding, our scientific understanding of the world in a virtual reality. So they can test hypotheses about how the climate system might change. And we can perform what-if experiments. We can say what happens if we carry on emitting greenhouse gases as we currently are, what happens if we make big reductions, what happens if we commit to the Paris pledges, what happens if we do more, and so on. And we can also look at other things as well, which I'll come back to. But these models, basically, we divide the world up into lots of little boxes. And then the equations are solved for those boxes. We what we call discretize the equations and solve them for the boxes. So, and we do the same thing for the atmosphere and the ocean. So in a weather model, you'd have a lot more boxes because you're only running it for a few days. In a climate model, you have to have much coarser resolution. You have far fewer boxes, so you don't get as much granularity. It also means you can't represent the weather quite as well. So it's a balance that we have to make. And we also do models which have more detail in them, but only cover a small region. So we use the global model to give us the boundary conditions, and then we use the regional model to give us more detail. So we can use a mix of approaches to try and compensate for the fact that we can't do everything. So this just gives a representation of some of the processes we need to represent, and I've talked about many of these already. The one thing to bear in mind is as well as the whole weather systems, and I mentioned about the ocean, we also need to have some representation of how the vegetation is going to behave. So, if trees are going to die, and so say your rainforest is going to disappear, we need to be able to represent that in some form in the model. Obviously, we can't represent every tree, so it's a crude representation of that. We also have to represent how the chemistry works, so how those different chemical species will react with each other in the atmosphere, and how that will influence the climate. So you can start to see the complexity. It also means that no single individual, certainly, and even institution can actually do all of this on their own. So most climate models, you'll find that they're developed with a whole range of collaborators to build in all that different science that you need to represent. When you think about clouds, for example, you can't represent the full detail of a cloud. If you look at this picture on the right-hand side, you can see, huge, interesting structures in those clouds. You couldn't possibly represent those in a box that's, 50 kilometers across or even 1 kilometer across. You have to what we call parameterize that. So you're kind of averaging the conditions. And so again, there's a lot of work goes into making sure that we do that in a credible way. to make sure that it reproduces what happens in the real world as well as we possibly can. So now I wanted to talk about how the carbon cycle impacts on climate. I think this is a really important part of the problem. And I mentioned that the ocean and the biology, basically, and the plants and so on, on land also absorb quite a lot of the carbon dioxide in the atmosphere, and indeed it obviously helps them to grow. In the short term, with small amounts of global warming, in some places plants are actually growing more effectively because they've got more carbon dioxide. It's only when you start to see the adverse effects of increased drought and so on that you get the negative effects. So it's quite a complex thing. But the amount of carbon dioxide that's absorbed by all those processes is dependent on temperature. As the temperature goes up, less of that carbon dioxide can be absorbed, and so more of it ends up in the atmosphere. And this is really well illustrated in this diagram. It's a very simple picture here. And you can see that where those peaks are, which the blue arrows are pointing to, those are where there are warm years, so you've got more CO2. So that's pointing to a problem in the future, that we get another positive feedback. I mentioned the water vapor one earlier, but the carbon cycle feedback means that as the temperature goes up, we can start to see an acceleration of the warming. And we're starting to be able to represent that in the models as well, but it's something that because we can observe it at this level, but not once we get 4 degrees global temperature, for example. How well do we understand that in our models? We can give possibilities of what might happen in the future, but once that type of effect starts to happen and the increases get much bigger, then it becomes very difficult to model. So we hope to avoid getting that to that situation, of course. Just another example of how we use the models to characterize the observed changes in climate, and that we can say that which ones are due to natural changes and which ones are due to man-made changes. So if you took a look at the two graphs, first of all, the graph at the top, the black line shows the observation, so that's the same on both graphs. The red and blue lines and the yellow lines are models. So the red and blue are average of the models and the yellows are individual models. And what you can see is on the top one, with just, if you assumed that there'd been no increases in greenhouse gases, you just took the ones that there were in before the Industrial Revolution, then you basically get no increase in temperature from the 1950s onwards. If you include the greenhouse gases, then you do get that increase. So that's a very clear signal at that global level. The changes are linked to man-made greenhouse gases. On the right-hand side, we can see that kind of translated into a map. So we have the natural forcing at the top, and you can see that there's really, it's around zero, essentially. There's kind of small changes, but when you average that over the time, it's pretty small. The observed trend, you see this warming, particularly over land in the Northern Hemisphere. The warming is greater over land, largely because, as I mentioned before, the ocean can absorb a lot of heat. So when you look at the surface of the ocean, you don't see it. You don't see the temperature increase to the extent that you do over the land. When you look at the models, you can see, again, you're getting more warming over Northern Hemisphere land. Oops, sorry. It's not exactly the same as the observation, so there are still some things that we need to understand better. So it's worth bearing in mind that we can't actually get all the details right. What we can do is give possibilities of what will happen, but we do know on a global scale that we're getting these changes. And by looking at these maps, we can get a fingerprint of what the global warming is doing. So as well as things like carbon dioxide, we can also look at things like the aerosols. You remember the things I said were cooling the atmosphere? We separate those out. We see a different fingerprint for those. And again, that gives us more confidence in what we're saying. So I just wanted to illustrate this in the historical context, really. And this is obviously looking at proxy measurements going right back to tens of millions of years before the present, and comparing that with the sorts of changes that we expect over the coming centuries. And what you can see by 2100 is the sort of, if we have a business as usual scenario, which is that red shading, so that's the kind of average model, and this is the range of possibilities. If you carry that across, you can see we're going back 3-4 million years before we see temperatures at that level. Once you get to 2200, you're going back 40 million years. So these are unprecedented changes that we're predicting. And so that's just really to give you an idea of the scale. And obviously, sea levels were massively different at this stage, tens of meters different. And We won't get that kind of change in sea level by 2100 because it takes a long time for things like the ice to melt over the Arctic and Antarctic. But you could, so it's because it's a transient problem, it's a changing problem. Some things will change more rapidly than others. So the temperatures will change more rapidly. Ice will change a little bit more slowly, a lot more slowly, I should say. So just to give you another illustration of this, and hopefully you can see this video, you can see that what we've done here is normally this video would be the temperatures going up from a global, so there's a global climate model and looking at the temperatures going up over a period of, I think, 200 years, 300 years. But what it's doing is instead of showing temperature, it's showing the comparative time when that temperature was the same. So we've just got to, so going back, so this is going forward through the 21st century. You can see you're getting yellows, oranges, green, gradually moving to red. So the orange is 4 million years ago, the yellow is 4 million years ago, the orange is 50 million years ago. So you can see how we're making that change. Again, it's not the same everywhere in the globe. You're seeing different amounts of warming in different places. So that's just another way of looking at it, I suppose. So obviously this science, there's a lot of interesting science here, but this is not about science. This is about how we need to respond to it. And there's obviously been huge, international negotiations, and those are underpinned by the Intergovernmental Panel on Climate Change. So this is not a political panel. It brings together all of the world scientists, science results in a series of reports over time, and those reports are then used by the negotiators to underpin their negotiations and decide how they should respond to climate change. So in 1990, the first report was produced saying that emissions resulting from human activities will enhance the greenhouse effect, resulting in additional warming of the Earth's surface. So the statement is there. They were deliberately very cautious to make sure they only put things in that they were absolutely sure about. Also, it had to be agreed by an international panel at the end. So again, that sometimes tones things down a bit, but you'll see as it goes on, the statements get stronger and stronger. So in 1995, the balance of evidence suggests that there is discernible human influence on global climate. 2001, most of the observed warming over the last 50 years is likely to have been due to the increase in greenhouse gas concentrations. 2007, there's very high confidence that the net effect of human activities since 1750 has been one of warming. 2013-14, and there's a study, there's one due out very soon, the next IPCC report. The warming of the climate system is unequivocal. It is extremely likely that human activities are the dominant driver of warming since the mid-20th century. It's interesting when people hear the climate discussion, they say, oh, nothing changes from one report to the other. But when you look at those different statements, they're all saying basically the same thing, but the strength of the statement is so much stronger by the time you get to 2013. We're saying, there's no doubt about this. You really can't argue with this. This is what is happening. Now, they're not saying, it's 100%, because scientists will never say anything's 100% because it never is. But you can't get a much stronger statement than that. I'm not quite sure what they're going to say this time, because I'm not quite sure how you'd say something even stronger than that. But they will have more evidence, of course. So how do we use this information? It's all very well tearing our hair out and saying we need to do something about climate change, but what do we do? And I think there's two aspects to this. One is, what do we do to reduce emissions? But the other is recognizing that the climate is changing. Even if we reduce emissions to zero, we'll still see some change, because I didn't mention before, but carbon dioxide has a lifetime of 100 years, which means it can stick around in the atmosphere for a very long time. And so the CO2 that's already there will continue to warm the atmosphere for some time. Excuse me. So we need to adapt to climate change as well. So we need to understand how the climate is changing so that we can make sure we build big enough flood defenses, look at how our agriculture might need to change, all of those things. These are just some extreme weather events. They're not particularly recent now, but they're quite striking. And there's a question here is, were these events caused by climate change? Some of you will remember Superstorm Sandy, for example, which was a tropical storm that headed northwards along the US coast and caused severe flooding in New York. That picture was on the front page of the Times, actually. It's so iconic you don't even need to really say where it is, but there are many other examples of extreme events. Now, you can never say a particular event is caused by climate change, but what you can say, as I mentioned before, was that these events are made more likely by climate change, and we can actually start to quantify how much more likely, and I gave an example of that earlier. So, but what we can also do, so this is a study that was done by a series of researchers in the UK, and they looked at the impacts of 4-degree warming and the impacts of 2-degree warming. So we can get an idea of what we can, even it's not a question of you fall off a cliff at 2 degrees, things happen at 1.5 degrees, things happen at 2, things happen at 4. What difference does it make if we reduce from 4 to 2 degrees? And what they showed was that between about 20 and 70% of impacts can be avoided by staying within 2 degrees. So because it's non-linear, some things are much bigger at 4 degrees. So it's really worthwhile making that reduction. And these are just some examples of the sorts of things that they looked at. So, for example, river flood risk on a global scale. At 2 degrees, it will affect 60 million people. At 4 degrees, it will affect 880 million people. And on the UK scale, you've got more heat waves affecting heat-related deaths at 2 degrees, but a 3-fold rise in deaths at 4 degrees. Of course, you also get far fewer deaths because of cold. So, there are some things that you need to look at this in the context of everything else. But there are many examples there. So this is quite an old picture now, actually, but what I wanted to illustrate is how our approach to adaptation and mitigation might change the landscape. So this is a farm landscape in 2000. It seems to be notably absent in terms of kind of wildlife. It's very much an agricultural landscape. Some of my environmental colleagues would call it an environmental desert, but and if you look now at 2050, what you see is you've got northward movement of crops. So here we've got sunflowers as an example. We've got new energy sources such as wind farms, and we see quite a few wind farms in certain parts of the country more than others, particularly offshore, of course, but some onshore as well. Farm-scale biofuel they're talking about here, and they've got production of biofuel crops. Now, as I say, this diagram was produced some time ago, 20 years ago, actually, and I was trying to find something similar that was a bit more up-to-date, but I couldn't. But one of the things I would say about this is that I think there's a growing realization that the large-scale growth of biofuels is a big issue because it takes up a lot of land, and that could either be used for growing crops or it could be used for wildlife and what we call ecosystem services. So a lot of carbon, and from a carbon point of view, it's an issue as well, because a lot of carbon is stored in natural systems, forests, in good soil conditions, and in plants. And if we strip away those to grow biofuels, we can actually increase the amount of CO2 in the atmosphere, and I will come back to this later. So I think big reliance on biofuels we need to be very careful about. There are some that you can use which are waste products from other things, which is a different matter. But I would like to see on this landscape something that also had an increase in the kind of wild landscape, which is obviously important for ecosystems, but it's also important for the climate system. So mitigation of climate change, and here are some examples of technologies that you all know about. So this is a piece of work that was done around the time of the Paris conference and of the climate conference. And what you can see here is that without any changes in policy, we're looking at increases in temperature of between 4 and 5 degrees by 2100. This is using models, of course. If we use the current policies, at that time, it was between 3 and 3.5 degrees around. And with the pledges that were made at the Paris conference, we're looking at 2.6 to 3.2. So if those pledges are implemented properly, then that's a substantial reduction. But if we really want to limit temperatures to 2 degrees, then we need to do more. And if we want to do 1.5 degrees, I think that would be incredibly difficult. And I'm not convinced, some of the things that you'd need to do might be more damaging than the problem. So there is a question about how much you would do, but we need to do so much more than we are doing now. It's kind of an academic question whether we aim for 2 or 3, 1.5 degrees, because we need to obviously do more. So moving on to how much this will cost. So again, this was part of the same study. This is a program called Avoid, actually, which I think the information is all available on their website. How much will decarbonisation cost? And this is an illustration of that we need to do something sooner rather than later, because the later you leave it, the more it costs. I mentioned that carbon dioxide in particular lasts in the atmosphere for a long time. So the longer you're carrying on emitting, the more you're building up that storage of CO2, and the more you need to drop it later on in order to compensate for that. So if we take action now, we're talking about 1.7% of global GDP. In 2030, we're talking 2.2%. But just to illustrate the scale, that doesn't seem like a very big number, 1.7%, but in terms of what's been done already, 4% is the fastest known sustained annual reduction of annual rate of decarbonisation. And we're looking at, if we start now, between 2 and 9% per year. So we need to be at least as fast as we've ever been, probably faster. If we wait till 2030, we're in a different ballpark. You know, it's twice as much, 3 times as much. So it really does help if we can do things sooner rather than later. And this is just an illustration of the types of technologies that you could use to do this. And what they were trying to do here is give plausible scenarios that get us to that point. And this is global. And if you look at the bottom of that diagram, you can see we've got, this is the annual average deployment rates of different types of energy production from 2000 to 2010. And so you can see you've got coal, 50 gigawatts per year, and then gas and nuclear, wind and solar. Now, so we're looking at a massive change. You look at 2020, we're looking at still using fossil fuels here, 80 gigawatts per year, but using carbon capture and storage. And in fact, there was some stuff in the news today about carbon capture and storage. Basically, what you do is you take, as you produce the electricity, the carbon dioxide that's produced, you capture it and bury it back underground. So perhaps where you've brought the gas out of the ground, or where you've brought coal out of the ground. So there is some technology. It's a very small scale. It needs to be scaled massively to do this. So it will be a huge challenge to do that. The next one, I think, is even more difficult because it's involving what we call bioenergy, carbon capture and storage, or BECCS. And the problem there is you've got to grow all these biofuels to do that. And I mentioned before that that could be an issue in itself. Large-scale nuclear and wind, obviously, and solar. Now, obviously, wind and solar have increased. But, you know, these are very big numbers. And then when we look, if we wait till 2030, of course, the number is much, much bigger. So again, we don't want to leave it any longer than we possibly can. So the other thing we need to bear in mind with all this is it's no good focusing on just one problem. And this is an illustration of unintended consequences. So this is air quality and climate change. I mentioned before that some of the particulates that are produced that have an impact on human health actually cool the climate. Now, when the government was looking for ways to decrease the carbon emissions in the early 2000s, they thought that one of the things that they could do was reduce the use of in cars and increase the use of diesel, because diesel it doesn't produce as much CO2. So much greenhouse gas, I should say. And so but they didn't worry too much about the pollution effect and the impact on human health, because the manufacturers told them that they could reduce that. But it illustrates, because what happened was, of course, that the diesel did produce a lot of pollutants, and that's caused significant problems, particularly in our cities. So it wasn't a very good solution. So what we need to do is look for solutions that are in this space here, in the beneficial for both air quality and climate change, the top right-hand quadrant, the things that help everything. So the things that will improve the Sustainable Development Goals, the things that will improve carbon, the things that will improve air quality. So reducing energy usage, increasing use of renewables that are less polluting, low emission vehicles, carbon capture, you know, all of those things. And but it just illustrates that we can't look at one problem at a time. We do need to look at it in context. And climate models actually can help with that process, because they can look at some of those unintended consequences by putting all of the processes together. So another example was bioenergy, and I talked about this before, and let's just give some numbers behind the things that I mentioned. So most of the, and one thing to bear in mind is a lot of these IPCC scenarios, even particularly the 1.5 degree scenarios, say, oh yeah, it is possible with current technology to reduce the warming to 1.5 degrees. But that current technology that they're talking about includes carbon capture and storage, includes massive amounts of biofuels, and it's not at all clear that that is really feasible. These are theoretical, and we need to look at some practical solutions that will help with this. So in terms of the BECCS so far, there's something in the US which costs $208 million and stores 1 megaton carbon per year, CO2 I should say. Many of the scenarios require a global storage 1,000 times this. So you can see it's a huge, that would be a huge scale up. The impact on land use, typical scenarios need more than 600 gigatons of CO2 from BECCS by 2100. 5% of ice-free land mass used for BECCS could provide most of that, but that would have significant impacts on ecosystems. And I mentioned before that the conversion of land for bioenergy, you get big losses in soil and vegetation carbon storage. So it's really not something you should do lightly. Tropical forest, for example, the initial storage losses significantly outweigh the gains of BECCS. And I think it could take 50 years before you get back to where you started. So it doesn't seem like a very sensible option for a lot of reasons. And then there was a recent study by the Grantham Institute, which was published about this time last year, which said that the BECCS cannot deliver the scale of negative emissions required in current emissions projections. So it's really giving a warning that that IPCC stuff is perhaps got a little bit disconnected, and they need to look at it a bit harder. So in an ideal world, what we're looking for is moving from the top line here to the bottom line. So with business as usual, we've got high emissions, big warming, the red at the top of the thermometer. If we can transform the way that we use greenhouse gases or don't use them, we can, in the right sort of way, we can both achieve sustainable development goals, reduce greenhouse gas emissions, and limit global warming. So that's the ideal world. Hopefully we can get there. But we've been talking about this a long time. So here we have the annual global CO2 emissions. This is not the cumulative amount of CO2. This is the annual global emissions. So you can see how they've gone up over time. And we've been talking about this seriously since 1990. And in that time, the amount of CO2 emitted is more than the amount that was emitted in the whole of the time before that, since the Industrial Revolution. So we need to stop talking and start acting. Another example, we talked, I think, during the COVID epidemic, the first one where a lot of people stopped traveling. I think that's probably slightly less true now. We talked about, whether there's a step change in the way people were going to work after after COVID, and this is just to illustrate the small effect that the pandemic has had. So because the CO2 builds up over time, and so the water level, this is like a bath of water, but it's CO2 in the atmosphere, because it's been building up over time and not really getting out of the system again. We see the black line is where it was in 2019. The green line is where it would be where at the end of the pandemic, and then the red line is without the pandemic. And you see it's measurable but small. And so the pandemic on its own isn't going to do anything. Maybe it will change our attitudes, and that might do something. So what does it mean for the UK? So the UK has been very proactive in this area, and we have reduced our greenhouse gases over time since 1990. Our direct emissions, but of course there are embedded emissions in what we consume, because we've exported a lot of our industry abroad, so we shouldn't be too complacent about this. But in the 2008 Climate Change Act committed to reducing by at least 80% by 2050, and the recent announcement by the UK government was that they would reduce greenhouse gases to net zero by 2050. So that's a challenging target. But if you look at the Climate Change Commission website, they outline how this could be done, and there are credible options for the UK to do that. On a global scale, of course, it is more difficult, but it's good if we can show some leadership here. That's a good thing. So that what else do we have in the UK? Well, we have very good climate models, and this, I'm not going to go through the details because I'm running out of time, but this is just an illustration of some of the things that have been improved in the recent climate model produced by the Met Office, collaborating with other scientists in the UK and with other big centres around the world. It's a global effort. This particular model is used by the Australians, by the South Koreans, and by others. And they've improved the way the clouds work, which is really important for summer climate feedbacks, the way that the ocean works, the way that the ice shelves work. As I mentioned, ice is really important. When it melts, if land ice, when it melts, will increase the amount of water in the ocean, for example. So all of these things are important. And we can use these models to look at how the climate is changing in the UK and what implications that has for how we plan for things like flood defences and so on. So the headline figure for the projections that were produced a couple of years ago was that there's a greater chance of warmer, wetter winters and hotter, drier summers. This was similar to the results that they produced around 10 years ago, but there is much more detail now on those, helping people to plan ahead and also to understand that these are not predictions, they're probabilities, just as Fitzroy said all those years ago. So this is gives you an idea of the sea level rise. So if we go for a kind of 4-degree type scenario, high emissions, we're looking at big sea level rises, smaller sea level rises with low emission scenarios. And these just give the variations in different parts of the country. So there are some differences in different parts of the country. And it also takes account of geological changes as well as the greenhouse gas changes. So this is another example of how we can use climate model outputs to make decisions, and it shows a study that was done some time ago now for the energy sector. National Grid pulled this together, and it brought together energy companies and the Met Office to work on how climate change would impact on the infrastructure. So they looked at things like how underground cables would behave when the temperature went up, and transformers. This is not something a climate scientist could do because they understand the weather. It's not something that the engineers could do on their own because they understand the technology, but they're not so much the climate change. So by putting the expertise together, it's an illustration of how you can understand those things. And you can see basically as it gets more red, that means it's more serious a problem, and it's time going along the bottom here. So there's more red on the right hand side, as you would expect. So that's just a nice illustration of the result. Obviously there's a big thick report that sits behind this, but it's a very good way of helping people to understand it in a simple way. So I'm going to do a plug now for a new journal, which I'm editor-in-chief of a colleague in Australia, and this is a Royal Meteorological Society journal, so it's based in the UK, but it's international. And we're very much looking at this problem about how the different processes interact and how climate change impacts on other things, the implications of climate change for sustainable environment and society. And so any of you who are scientists, I would urge you to look at it and see whether you might want to publish in it, or if you know people who might want to publish in it. I think that I was really keen to get involved in this because I think it's really important that we bring together expertise to help to understand the problems. It's as science gets more complex, people get very siloed in their individual specialisms, and it becomes more difficult for people to work together to solve the complex problems that rely on all of their science coming together. And so this will help for people to be able to publish in that kind of space. So finally, I was going to just leave this up while I finish my talk, which is just showing the temperatures. You may have seen this before. I think it was even shown at the last Olympics, actually. And it's showing the temperature graph as a kind of, in a slightly different form. And so you can see how temperature is increasing over time and how we're rapidly approaching 1.5 degrees. In fact, in 2018, I think it actually hit 1.5 degrees briefly for the global average. So I will stop there and ask if there are any questions.